Okay, let's work through problem number 2 here. And the problem is actually referencing the equation from number 1, and we'll take a look at that in just a minute. I just want to point out some language here. So these are the barium nitrate and the sodium phosphate are the two reactants. It's telling you in the problem that you're putting in an excess amount of the barium nitrate. So even though the concentration is given here, that really doesn't matter. If you remember back from Gen Chem 2, we talked about, you learned about limiting reactant and excess reactants, and there's always those two things in a solution, if you will. And if it's telling you that the barium nitrate is in excess, then that means that the sodium phosphate is the limiting reactant. And just remember that when we talk about a limiting reactant, that's what's going to control what is produced in a particular reaction. And what we want to know are the number of grams of the product of this barium phosphate. Let's take a look at the equation up here. And so I'm going to go from, information about the sodium phosphate over to the number of grams of the barium phosphate. Let me use the space below to actually sort of lay out the information that I have in front of me. So I'm told that I have 25 milliliters of the sodium phosphate, and the concentration is coming in at 1.23 molar. That's all the information I have. Okay, that's fine, because in the first step of almost any type of stoichiometry calculation, you should ask yourself, how do I calculate number of moles? It may take a step or two to do that, but that's really ultimately what you're trying to get after. Because once you have the number of moles present, then you can use the number of moles along with the molar coefficients here in red to then switch between, in this case, the limiting reactant of the sodium phosphate and then of the product that we want to know about, right? The grams of this sample. And moles are not given in the problem, but they are embedded within that information, right? Molarity stands for moles per liters. I have a volume value. It's in milliliters here. Let's just go ahead and convert that to liters real quick. One of the more useful conversion factors from the metric system that you learned in Gen Chem 2 or Gen Chem 1 is going to be this guy. There's a 1,000 milliliters in 1 liter. And what that tells me is that the 25 milliliters is equal to 0.0250 liters there. Right, we're effectively taking the decimal 1, 2, 3 and moving it to the left 3 places when we divide by 1,000 there. How does that help us? Well, you can, something I talked about in class, there's this little equation triangle that is useful, right? It says just taking the typical molarity formula, molarity is equal to moles divided by liters, okay? If I want to determine the number of moles, then it tells me that it's the concentration times the liters. Basically, when you're moving left to right, that's multiplication. From the top to the bottom, that is division in terms of using the equation triangle. Let's do that here. I just said that moles is equal to molarity times liters. Let's put that let's put our data into the formula and see what we come up with. And instead of writing out the capital M for molarity, I'm going to use the units that are within that, if you will. Right? Molarity stands for moles per liter, and you'll see why I do that in just a second. If I then multiply by my volume in liters, notice what's happening here is that my units cancel out. So yes, we have a formula, but ultimately every formula, when you're working with multiplication and division in particular, it's really a dimensional analysis type of problem. If the units cancel out and you're left with what you're interested in, again, in this case, moles of the limiting reactant, then you are setting up the problem correctly. If I put this on my calculator, I get, and I'm going to use all the digits from my calculator here. So that's the number of moles of the limiting reactant. Okay, now that we have the number of moles of that guy, let's talk about how we then switch over to the product over there. So let me rewrite this. I'm going to add the sodium phosphate as basically a unit here. And I'm going to approach this from a dimensional analysis standpoint. Right? So what it means here is that there's, for every 2 moles of the limiting reactant that is consumed, I produce 1 mole of the product. So 2 moles of the sodium phosphate is going to go on the bottom. And the reason why I'm doing that is because I want to cancel out the moles of the sodium phosphate and be left with moles of the barium phosphate. The moles of sodium phosphate cancel out the moles of sodium phosphate, and I'm left with what I want here. So, right, these parentheses tells us what we need to multiply by, what we need to divide by. In this case, mathematically, I want to divide by 2 here. Now, if I went through this calculation, I would have the number of moles of the product, but I do want to, just for the sake of time and space, I want to go ahead and then use the molar mass of the barium phosphate to then do the final step in the calculation, which is determining the number of grams. Right, so the molar mass of this guy is 601. It's a pretty big molecule. Right? Remember, I just determined that by looking at the periodic table and looking at the average atomic mass for barium phosphate and oxygen. And notice what's happening here. I have 3 bariums, actually have 8 oxygens, and I have 2 of the phosphates there. Right? That 2 on the outside of the phosphate is distributed, if you will, to each of those elements inside there, coming up with a total of 601.93 grams per mole. Why do I multiply by this value here? Well, because by putting moles on the bottom and grams up top, then I get my proper unit cancellation. Right? Grams the only thing left over, which is what I want to know about. I'm going to write out more digits than is correct. I'm going to write out a bunch of the digits that my calculator gave me. And then I want to just make a brief point about the significant figures here. So when we're working with sig figs, we're just looking at the data that's given to us. It's really just those 2 data points. There are 3 sig figs there. There are 3 sig figs there. And since this entire operation was multiplication and division, the rounding off rule, or I should say the sig fig rule, is that we use the whichever number had the fewest number of sig figs. Now, since both of them have 3, then we're going to keep the first 3 sig figs in our problem. That 0 there is not significant. And then finally, if we want to round this off properly, this number is 4, and so we just really just drop that portion of the expression. And that is consistent with the answer that was given in the problem. And then the last thing I want to say is that really the proper way to do one of these calculations is to round at the very end. Okay, so I've carried through all of the digits, whatever my calculator is giving me as I'm plugging and chugging through the problem, and I don't round off until the very end. Okay, that's really the best way to approach any type of calculation in chemistry. And the final thing on the test, make sure when you have a mathematical operation that you're doing like this, on the short answer portion of the test, that you show me the work to receive full credit. Okay, thanks.